Hi, in today's tutorial we will learn how to segment dust storm from images using the U-Net VGG architecture. But first of all, I recommend you to watch this tutorial that do a similar thing on another U-Net efficient B0 architecture. Both tutorials give us the ability to do an image segmentation based on a pre-trained architecture like a VGG16 and efficient B0. Let's start with a short demo to see the target of this tutorial. So we will use a dataset of dust storm. So this is the dataset, you can see it here. Here are all the images, and you can see all these images are basically images of a dust storm. And also we have annotations, which are masks of those dust images. And after building our model, which is based on the U-Net VGG16, and train our model, we will get a save weights of this training process, and then we jump directly to the final result. We will take one image, this image, as you can see it's a dust storm, and we would like to run a prediction and create a mask for the same area and of the dust storm. So this step will conclude the inference process of loading the image, loading the saved model, running a prediction, and converting this prediction into a mask. And as you can see, this is the result. On the left side is the original image, and on the right side you can see this is the dust storm. It covers pretty well the dust storm in the original image. So let's jump directly for the installation and then for the coding. So before the installation, this tutorial is like a part 2 of my previous tutorial. If we go back to my YouTube channel and let's focus on this video, efficient B0, great accuracy on water mask. Basically it's the same concept. So we will start with building the architecture of our model, and then we will build our model based on this architecture. So in the first phase we will build the architecture of the VGG16, and you can reuse it on several use cases. So in this video, in my previous video, I really doing a step-by-step freestyle coding of each of the commands in the process. And in my next tutorial, in this tutorial, we will do a short brief of the code. So I will not type it during the video as my last video, but we will cover each of the commands, and you can download the code. It will be part of the video description. I will do a short brief and explanation of the parts of the code, but we will not do a freestyle coding, just cover the code. So the first process will be installation, and it's all covered in the install.txt file. We will create a new Python environment. Let's name it U-Net, and it will be based on Python 3.11. After that we will activate it. All this process will run on a Linux machine. I'm using WSL2 under Windows, so WSL2 gives the ability to install Linux on a Windows machine. So since I'm using Ubuntu, it will have the ability to use the GPU functionality of TensorFlow. So in the Ubuntu environment, you will run a pip install TensorFlow and CUDA, and I'm using TensorFlow 2.17.1 version. I recommend that we do you will use the same version, so we will get the same result. And there is also here a link for how to install TensorFlow on Windows WSL environment. If you don't have a GPU card, you can also run the same tutorial on a CPU. So this will be the command pip install TensorFlow equal 2.17.1. And after that, we have to install these three Python libraries. And at last, we have to download the dataset of the dust storm. So if we will jump to our browser, so this is the link for the Kaggle dataset website. I will leave a link in the install file directly to this dataset. And if we scroll down, you can see there are two subfolders. One is images and the second one is annotations. You should download the dataset to your local machine. I already done that, so let's jump to the dataset folders. If I open the images, you can see there are several images of dust storms, so many images of dust storms. And after that, you have another subfolder named annotations, and here all the dust storms are annotated and segmented using white as indicates the object and black indicates all the rest. As you can see, we have about 80 images, so we will use a process of augmentation in order to create more images for the training. Let's move it aside, let's minimize it, and let's jump directly to the first Python code. Let's start with covering the first Python code. As you can see, it's named VGG16_U-net.py. So this code can be reused in all the segmentation use cases. So it's not specific to our dust storm use case, and you can try to use it in different use cases and segmentation problems. So let's start. First of all, we will import process. We will import all the keras layers that we need in order to build our unit network. We will use convolution, batch normalization, activation, pooling, upsampling, concatenation. So these are first of all the import process. And after that, we will pull in the keras model class. Here it is, the keras model class, so we can wrap the whole network as a single object. And after that, we are bringing in the classic VGG backbone already trained in the ImageNet, so we can use it as our encoder. Now we will create an helper function, a double convolution block. Here it is. 2 3x3 convolutions, each followed by a batch normalization and ReLU. And this is the basic built-in brick of both encoder and decoder. If you jump inside, you can see here is the first 3x3 convolution, no stride, same padding to keep spatial size. Then we are, this is the batch normalization to help speed up training and add stability. And here we are using a ReLU to inject known linearity. And here we have the second 3x3 convolution, same pattern for feature representation. And we are returning the process tensor so the caller can keep stacking. Let's go to the next function, which is the decoder. this helper function is our decoder block. We upsample with transpose convolution, concatenate the corresponding skip features, and refine with convolution block. If we go inside, you can see here that we are upsampling the feature map by a factor of 2 using conv2d transpose, and here we are stitching the encoder skip feature to retain high resolution context, and here we are running the combined tensor through our double conv block for cleanup. And after that, hands the refined feature back to the caller using the return x. And now this is our main function. This will be our main builder that fuses the VGG16 as encoder and custom decoder for the full U-Net. We will start with creating the model input with the shape we are receiving images in. We are here loading VGG16 without the fully connected top, reusing ImageNet weights for a strong start. And then, as you can see here, this is grabbing key layers for skip connection, block 1 conv2, output spatial size 512 at this resolution. And now we are jumping to the bridge. This is the deepest features before we start decoding. And at last, this is the decoder. And each step doubles resolution and halves the channels. And at last, this is the output: one channel mask with segment activation. A funnel 1x1 convolution forces the channel dimension to 1. And in this function, we are wrapping everything into a keras model we can compile and train and return the model. We are hand the model back to whoever called this function build VGG U-Net. And at last, this will help us to run it and to see if everything works well. It's a script entry point, so we can run this file directly. Great. The next step will be dealing with our data, preparing our data. Once again, I recommend to jump to my previous video where I explain each of the lines and run it during the coding. And in this tutorial, I will cover the code and run the full process after the explanation. So let's start. As you understand, the mask is binary, so the pixel value 0 means background, 255, which is a white color, means water. And so this is a short explanation for dealing with the mask. And then we will import all the relevant Python libraries that are participating in this process. Next, we are defining the target resolution for all images and mask. Feel free to change the values. You can enlarge it, duplicate if you have more GPU resources. I run it here on with a 128 by 128, means that all the images will be resized to this dimension. Next, we will create an empty Python list that will eventually turn into a big NumPy tensors. This list will contain all the train images, these contain all the mask train images, and this will contain the validation images and the validation mask. These are the paths to our dataset. This is the path for our main folder, and under it, inside, there are two subfolder images and annotations. Now let's do a sanity check on one image, image number 13. So we will load the image and its corresponding mask, and let's do some manipulation on these images. As you can see, this is an RGB image and this is a grayscale, means only a black and white image. So let's create a figure and set the subplots. We are going to do a side-by-side visualization to confirm that everything is lines up. After that, we are plotting the first image. This is our original image, and next to it we will demonstrate and display the mask. And this tight layout means that both images will be one next to each other, and we will display these two images as a one image. So this will be the first process. You can run it and expect to see the image and its mask. And after that, we will do a tiny experiment. We will shrink the mask to 16 by 16, so we will pick up the raw pixel values. And if you will print it, you will see that the values are sometimes 0 and sometimes 255, but sometimes there are values, let's say, between those values. So we would like to change all the values, that all values above 0 we will be replaced with the value 1, and all the values 0 we will stay 0. So in this case we will display more clear the mask in a 16 by 16 image. So basically in this command we are converting the mask from 0 to 255 to a clean binary 0 or 1 image. And once you will print it, you can see the result. After that, now we are ready to try some augmentation, and the target of the augmentation is creating more images for the training. As you can see, we have only 80 images, and we would like to create more images out of the original dataset. So first of all, we will do a horizontal flip, and after that vertical flip, and after that we will do a random rotation between minus 50 degrees and plus 20 degrees. So basically we will take one image and create out of it 3 more images. So we will have 4 images that are basically the same image but have a slightly different, like flipping the image and rotating the image. And in this process we are displaying the result of these extra 3 images. Now after that, after we played a little bit with one image, let's deal with the whole dataset. Now it's time to dive into the full dataset and crank out the image mask pairs. So first of all, we will do a listing of every file in the images and in the mask directories. And let's print the results. Let's print it here, then we will get the amount of those images. We already know that there are 80 images. Now let's go for this processing loop. This loop function will run through all the images list. The TQDM will help us to see the progress bar while looping through all the files. We will build an absolute path for the current RGB frame, and here we will craft the corresponding mask file name, and we will replace the .gpg with underscore gt.gpt, and here we will load and resize and normalize the image, and after that we will load and prepare the mask in grayscale, and now we will run an augmentation for all the images in the loop process. We will do a data augmentation like horizontal flip, vertical flip, and rotation, so for each of the images. And here we will print a summary of how many samples we ended up with after the augmentation. We already know that each of the images will become to 3 more samples during this process. After that, we will convert Python list into a NumPy arrays in a TensorFlow. It will help us for the training, and we will print the shapes of those NumPy arrays. So we are expecting to see the first value will be how many images, and then the shape of each of the images. And at last, we will preserve all the data. We will store the dataset to our local disk so we can load it instantly in our next time. So let's run it and see the result. So first of all, as you can see, this is our original image, the image number 13 if you remember. So we just loading the image and loading its mask. So the mask indicates the storm dust area. Let's continue. Now, as you can see, this is the 16 by 16 that converting the mask. So the 1 indicates the mask and the 0 is all the rest. And the next phase is displaying the augmentation. So this is the original image. This is the horizontal flip. This is a vertical flip. And at last he is doing a random rotation. And now we are running for all the images. As you remember, we have only 80 images. So as you can see here, we created 320 images. So each of the images was duplicated 3 times in a different augmentation task. And also we save our dataset. So now we are ready to continue to the next step, which is building our model and training. Now let's continue to step number 2, which is building our model and training our model. We will start with importing the necessary Python libraries. And after that, we are loading the pre-processed NumPy file that we saved in our previous notebook. And we are loading it into these 2 variables, all image np and mask image np. So here we are expecting to see 320 images and mask. After that, we will print the shape and we can do a sanity. We can inspect the tensor shapes to confirm that the load worked. Next, we will split the data. We will split in the data into 80% of training and 20% validation for our training. And we will do a quick printout so we can see the new dimensions and new NumPy arrays. And we will choose the same dimensions as preparing the data, 128 by 128 for each of the images and mask. Next, we will import the relevant TensorFlow libraries and objects. Please notice that we are loading this function from this Python file, the one that we created in the first step, the one that can be reused in many other segmentation processes. So here we are defining the hyperparameters tuned for a GPU. This would be our learning rate. Our bet size would be 4. If you have more GPU power, so you can make this value like 8 or 16, you can enlarge this value, and we will run it to 200 epochs, and basically it's plenty of epochs because we are adding an early stopping, so we will stop the process. It will not run the full 200 epochs, probably it will stop earlier. Now we are building the VGG powered U-Net from our helper function. You can see it here, and it's always nice to see the parameter count and see if our model was built correctly, so we will print the summary. We will use the Adam optimizer with our chosen learning rate, and here we are defining a binary cross entropy as perfect for single class foreground background mask. And here we will calculate two values. We will calculate the state count for the Keras fit, so it knows when an epoch ends. Next, let's define the name of our saved file for the weights during the training. And here we will set in 3 callbacks, and the most important is here the early stopping. The early stopping is covers 20 epochs of patience. If there will be no progress during 20 epochs, the model will stop the train. And of course it also detects if there was improvement, and each time you will find an improvement, it will save the best model to this file. And here, this is the process of the training. This is time to launch the training loop, and this is where the magic happens. As you can see, all the parameters all the arguments are sent to our fit function. The training data, the validation data, how many epochs, the bet size, etc., etc. And at last, we will show the result of the training. We will chart accuracy and loss to visualize our convergence. First, we are pulling the metrics out of the history object for plotting, and here we are displaying the training and the validation accuracy, and here we are displaying the loss chart of the training and validation. And I think we are ready to start the training, so let's run it. So the data is already loaded, and here we are on the first epoch. And let's wait a few seconds and we will see the movement, the progress of the training. Great, as you can see, this is the first epoch. You can see here that the model was saved to this file. Now it's running the second epoch. You can see that the values was improved, so it's once again saving and storing and override our last weights, and this is the epoch number 5. You can also see the progress of the loss. You can see here that the loss is going down, so it indicates a good process. Let's see here the validation loss. I think it's more important. We start with validation loss of 1.5, and here is 8.0, 8.6, 8.4, and 8.44. So the process it indicates that it's a good training. So let's stop the recording now, and we will continue after the process is finished. So as you can see, the process stopped after 33 epochs, and as you can see the results, it's not a perfect result, but you can see that the accuracy, the training accuracy and the validation accuracy are basically in the same progress. Let's see the validation. There is a spike here. It's not a good spike, but I think this indicates a good result. Maybe I should add more patience time for the early stopping. Maybe we will add it to 30 or 40 and we will get more time of training. But it's good for now. Let's try to do some prediction and inference of our model. Now let's cover our last Python code, which is running an inference of our saved model. So we will start with loading our these Python libraries, NumPy, TensorFlow, OpenCV, and Matplotlib. Then we will load our saved model that contains the best checkpoints we saved during the training, and let's print the model summary. And this is optional, just to love and see that our model was loaded successfully. Let's define the same dimension, and this is our test image. As you can see, it will be here part of the code. This is our test image. We will use this image for the inference process. So this is the path for our image, and we will load this image using OpenCV and convert the image to RGB from BGR. And next we will do some pre-processing. We will resize the image to 128 by 128. We will do a normalization here, so the values of the image will be between 0 and 1, and we will add a batch dimension with the value 1. That means that we will create a batch of images that contain only one image. Our model expecting a batch of images. Then we will forward this image, this converted image, and pass it to our model. We will do the prediction process, and after that we will strip off the batch dimension, and let's print it and see the result. So since it's a binary classification, so all the values above 0, this means basically that it's a value of 1. A value of 1 indicates our object, and every value under 0.5 will predict it as 0. So we are creating a mask that 1 indicates our object and 0 indicates our background. And since we would like to display it as an image, we will convert all these ones, all these values above 0.5 to 255. That means a white color. So the object will be white and all the rest will be in value 0 that indicates black. And for a nice side-by-side display, we will shrink both images by 25% for our original image, and let's store the result. We will save the result to our local disk, and after that we will create a figure that on the left side we will display our original image, and on the right side we will display our predicted mask. And I believe it will be more clear after we will run this prediction. So let's load our image, convert it, normalize it, and display it with our prediction side by side. Great. As you can see, on the left side, this is the original image, and on the right side, you can see it's a very good prediction of the dust storm. Once again, I believe that if we will put a higher value for the patients during the training, and give it more time to train more than 30 epochs, let's say more close to 100 epochs, I will believe that the result will be more accurate and it will generate a better mask. But as for this tutorial, I think it's good enough, and you can grasp the concept of how to create a segmentation process using VGG U-net. So thank you very much. You are most welcome to subscribe my channel. Bye bye.